All right, welcome linear algebra students. In this video, I'm going to be showing you a little bit about using the calculator for row reduction so we can speed up a few things. Maybe you've got a test coming up, or maybe you just need to know how to use technology to speed up the row reduction process. So the first example I've got for you is, going to give you a situation. Let's find a third-degree polynomial that passes through these 4 points. Okay, so what we're going to need to do is we're going to need to set up a system of linear equations, and I'm just going to do that. All right, so notice how I took the point x is 0 and f of x equals 4, and I plugged it into that equation up there, that kind of generalized formula for a third-degree polynomial. And I did the same for the point 1, 3, 2, 2, and negative 1, right there. Okay, that gives me 4 equations and 4 variables. And if I were to kind of like clean these up, well, I'd have 0a plus 0b plus 0c plus d. Okay, so I'm just going to say, I know that's going to be 4 equals d. Now I'll keep that in my matrix to maybe make it go a little faster. That would be fine. And now I'm going to kind of clean up these numbers and the letters and make it more like something I could turn into an augmented matrix easy. All right, so that's a little more cleaned up. And we can turn this into an augmented matrix that we will want to row reduce, and we'll have 0, 1, 8, negative 1. And on B's we'll have 0, 1, 4, 1. C's will have 0, 1, 2, negative 1. And for D's, I'll have all 1s. And then I'll be augmenting this with 4, 3, 2, and negative 1. And so what we want to do is we just want to row reduce this matrix. So I'm going to pull up a matrix, going to alpha and F3, and I'm going to click, I want a 4-row by 5-column matrix. Okay, and then I'll come around and say, okay, give it to me. And now I'm going to fill in all the numbers, but I don't need you to watch me do that. All right, there you go. I plugged these all in. I'm realizing now that, okay, I need to go all the way up to the left because I didn't tell it to do anything. So I'm going to need to insert a command, like a reduce row echelon form command. And what we do, we get that by going to matrix right here and going into matrix math and scroll down until we hit the reduced row echelon form. So we'll do that. You don't need a back parenthesis here. If it makes you feel better, you can scroll over and put that in. But then I'm going to get this. So what the calculator's telling me is that, this row reduces to that matrix, and I've got A equals 1, B equals negative 3, C equals 1, and D equals 4. Meaning that, okay, my polynomial that I've been trying to find, is 1x to the third minus 3x to the 2 plus 1x plus 4. Okay. And that's how we did that one. Now, let's express a vector as a linear combination of some other vectors, which, as you know by now, is equivalent to solving a system of linear equations, right? So the question is, how many how many A's plus how many B's plus how many C's is equal to 6, 6, negative 2. So what that's going to be like is just taking A, B, and C, making them the columns of a matrix, augmenting it with 6, 6, negative 2, and row reducing. Okay? So what I'm going to do is I'm going to make myself an augmented matrix, and it'll be 1, 2, 1, 2, 3, 0, negative 1, 0, negative 1, augmented with 6 and negative 2. Okay? And now we need to row reduce the thing. So I'm going to go over here to the... Okay, so I've got my matrix in there all set up. I'm going to row reduce it using technology, and then there we go. All right. So now I'm seeing that x1 equals negative 3, x2 equals positive 4, and x3 equals negative 1. So if I'm going to express the vector as a combination of the others, I'm going to say that 6, 6, negative 2 is equal to -3 of A plus 4 of B, pardon me, minus 1 of C. Okay, I'm going to do a couple more examples for you. First, I'm going to ask you, is this matrix non-singular? Okay, so when we hear that, we know that we need to be investigating the solutions to AX equals 0. So what we do is we're going to augment A with the 0 vector, row reduce the thing. All right, so I've augmented A with the 0 vector. I'm going to row reduce the thing. And I'm going to get, oh, hey, look, I've got non-trivial solutions. Okay, I really didn't expect that to happen. I just made these vectors up on my own. It looks like I happened to choose a dependent set of vectors. I didn't expect that to happen. But I see now that column 1 plus column 2 is equal to column 3, which I probably should have seen that coming. I was just making numbers up. Okay, so I'm going to say A is singular because, let's see, if x1 plus x3 equals 0, so x1 equals negative x3, and what else am I saying? x2 equals negative x3, and x4 needs to be equal to 0. Okay, whatever. Okay, because x equals, and I'm just going to choose x3 equals, we'll say -1, right? So it'd be 1, 1, -1, 0 is a non-trivial solution to AX equals 0. Okay. All right, the last example I've got for you is here's a set of vectors. Is it linear independent? Right? So we know what we're going to do here. We're going to kind of figure out how many, so x1, if I called this v1, v2, v3, how many of v1 plus how many of v2 plus how many of v3 gives me the 0 vector. And I mean, I made these up again, but hopefully with any luck, these will be independent. I tried to think a little harder about it and make sure they weren't. Okay, so we're going to reduce row echelon form a 3 by, and you know, maybe I know that if I augment with a column of zeros, right, it's like not augmenting with anything. I can mentally augment that at the end. 1, 2, 1, 0, 1, 0, 1, 3, 3. And I'm going to hope for the best. There we go. All right. So the only solution, because I'm like, you know, kind of mentally augmenting right here with a 0 vector. That means x1 has to equal 0, x2 has to equal 0, and x3 equals 0. Meaning that this is a linear independent set. Also, you know, if I was to ask you about the span of these three things, and I'd already found that it was independent, I'm going to just say that the span of S is equal to all of R3. Okay. I'll let you think about why that's true.